In previous lecture, we have talked about linear algebra. We have completed a chapter in Math for AI, linear algebra. We started with theory. We have covered most concepts there, like eliminations, transformations, spaces, square matrices, non-square matrices, and we studied the most important concepts which are required for machine learning, which is eigendecomposition and singular value decomposition. And from these two concepts, we have built machine learning methods. Right from the theory concepts, we have built machine learning methods called principal component analysis and SVD based implementation. And we have coded that as well. Like we have taken a real world example of n-dimensional data, reduce it to two or three dimension, and we have seen what is the pattern that n dimensional data is telling us, and along with it we have built a movie recommendation as well. Now we are going to start another chapter, and the name of the chapter is calculus. So let me write it out here, calculus. And I want to cover calculus in such a way that, like, if you take calculus, we have integration, we have differentiation, and in that we have like different concepts like partial derivatives, like different concepts of like integration. So it's a very huge thing in itself, and to cover entire calculus, it will take us for probably 3 or 4 weeks. So I don't want to spend that much of time. What I will do definitely is that I'll cover the theory topics which are necessary, which are required to understand the working of AI in depth, right? And let me tell you this, linear algebra is like the foundation. It starts machine learning, but calculus is the place from where we begin our journey of neural networks, where we start understanding how AI is actually connected with math. So this is going to be really important, and I want you to have like complete clarity in each and everything which I'm speaking. If you have any sort of doubt, please interrupt me right away and ask like what your doubt is and why you're not understanding it. Because if you miss one concept, then it will go into a loophole and you will end up not understanding the concept, and you might feel difficult. So if you have any doubts, right away raise your hand and I'll be more than happy to answer what is your. Okay, so in calculus, the first topic we are going to study is the derivative which trains neural network, right? This is the title of our lecture. And to begin with, I want you to have idea on one thing, which is what is the working of a neural network. This is our zero topic, which is the foundation of the entire lecture. If you don't understand it, then it might be hard for you to understand further topics. So I have a proper understanding of what I'm telling, and this is like 30-second picture which you have to understand. Okay, so the question I want to ask is, we might have heard hundreds of times, like people talk about like GPTs are trained, all AI models are trained on neural network and so on. But what does a neural network actually do, and what is a neural network? That is my question. So the first question I'm asking is, what is the work of a neural network? What is the work of a neural network? Let me write it down, and I want you guys to have this in your notes. The first work is, it predicts. A neural network okay predicts output, comma, gives answer. You can say predict output or give answer, it's the same thing. And what it will do is that it compares that output, it compares that generated output. Okay, imagine like it takes input, it does something. We don't have to care right now what it does, what it will do generally, but it do some sort of math, and after doing math, it give you output, right? What we do is that neural network, what it will do along with giving output is that it compares that predicted output with respect to true answer. We will talk about like what is this true answer, where does it come from and all. But remember, First, it generates output. After doing some math, it generates output. Number two, it compiles that generated output, that predicted value, with respect to true answer. It asks like, how far am I? A neural network asks itself like, how far am I from true answer, right? And what it will do is that after asking, like after getting the value, how far it is, this value, like how far, whatever the value we get, right, the distance, you can imagine as a distance or a number, whatever it is, we represent this like true answer and the output generated, whatever the distance gap there is, we represent it with a number, right? And we call this number, whatever the number it is, whatever the representation we use, that representation is known as loss. Okay, I will talk about definitions, I'll talk about all the things, but for now understand that it will take an input, it do some math, and it will give you output. Then after giving output, it compiles that output with the true answer, and whatever the gap is there between the generated output and the true answer, we call that gap as loss. Okay, now it tries to minimize the loss by changing something called as weights comma biases, right? It change something, and that something is weights and biases. I'll talk about what is it, I'll talk about what is loss and all. There's few terminologies which is necessary, I'll talk about them in few minutes, but try to understand that it predicts output, compiles that output with the true answer, and to minimize that loss, we change something which is internal, something which is a part of neural network, and that is weight and biases. And this is the work of the neural network. These are the three things which every neural network does, whether it is built by Anthropic, whether it is built by OpenAI, whatever the organization might be. But these three things are fixated in every neural network, and this is how a AI model works. A large language model works, right? It predicts output, it like compares that output to the true answer, and if it is not matching, then it changes something inside it, and that something is weights and biases. We'll try to alter that, and after changing we what happens is that that output and the true answer will minimize, the gap between them will minimize, will go towards the right answer, right? And that is our goal. We want our neural network, whenever we give a set of input, it should predict the right answer. I'll give you an example, I'll give a very like simple example. Let's say my example is uh, Mars is a dash. Okay, so I have given my neural network these three characters, and I'm expecting that my neural network will give me output, right? And I know that my true answer is Mars is a planet. Now, how I will compare whether my output is near to true answer or whether it is far away from true answer. Okay, so understand this. If my neural network gives you Mars is a Taylor Swift, then it is very far away when compared to Mars's space, because space is correlated to planet. So you can say that this answer is near to planet when compared to Taylor Swift. Taylor Swift is completely random, right? So the distance of this answer 1 is more when compared to this answer 2. And our goal in this entire lecture is to minimize the gap. I have told you, right? We alter, we nudge the weights to minimize this answer, to go from Taylor Swift to planet. We go from very wrong answer to true answer. We want to minimize this loss. We want to go from wrong answer to right answer. And to minimize that, we nudge our weights and biases in such a way that the loss we get should be minimum. And how we are going to do that, how we can tell that, like let's say I'm changing my weights and biases. How can I tell that in which direction I have to change, whether I have to increase or whether I have to decrease my weights, and how much I have to do, right? So the question comes, this is our goal. We have understood our goal, right? We want to change our weights to minimize our loss, but how and how much, right? In which direction? The question comes is, in which direction do we need to change? Should we increase or should we decrease our weights, and how much we need to change that to exactly go towards right answer, to exactly sit on top of right answer, right? How much we need to change our weights comma biases, how much? So this thing, in which direction and exactly how much, is answered by a derivative, is answered by a rule which we have studied in 11th class, 12th class, I think in high school as well, when we study differentiation. And that thing is chain rule. Chain rule will tell you that how much you need to change your weights, how much you need to change your biases, and in which direction you need to change. Okay, by following chain rule, you can exactly know, on top of your neural network, how much weights and how much biases you need to change in order to minimize loss and get to the true answer. That is our goal. So I will explain you how to find this and how chain rule is important, how chain rule is useful here. And let me tell you this, remember the definition, some definition. So here, if I'm talking about one neural network, then I'll say that I'll apply chain rule. If I'm talking about a complete millions of neural networks, right? Millions of, like thousands of neural networks, then I call the same chain rule as back propagation. Okay, remember, if chain rule is being applied on a huge network, then we call it as back propagation. Simple. So this is the first picture I want you to understand about neural network, what it does and what is our goal and how we are going to get to that goal using the concept of calculus. Okay, clear. And one more thing. I know that for newbies who don't know anything about neural networks, weights, biases, I want to introduce them. The understanding of vocabulary is really important. So the vocabulary, let me start with the first terminology. I want you to write it down in your notebook. These definitions are going to be the foundation of our entire lecture. If you don't understand this definition, please ask right away. Okay, so the first thing is you need to understand what is a function. And if you ask me, Jabir, for you, what is function? For me, the definition of function is, I imagine function as a magic box, as a machine, right? It's a box, and for this box, you give it some input and it will give you some output. That is it. That is the meaning of function. That is a definition of function, right? It is a machine which takes some input and give you some output. Yes, if you study mathematics in detail, then there might be hundreds of properties, different properties related to function, like one to one, on to different types of properties are there. But for now, they are not needed. What is needed is this understanding that it's a magic box which takes input, which takes certain input, and it will give you a output. I can give you example. For example, let's say my function looks like something like this. F of x is equals to x square. Then if I have to visualize, then imagine this box as f of x. Okay, and it takes what it will take. It takes x values and it will give you x square value. For example, if my x is equals to 3, then my input will be 3. It will go into f of x box, this magic box, and it will give you 9 as output. So what this function tells me? This function tells me that whatever the number you give, it will return the output as square of that input number. Okay, so this is the meaning of function. Function is basically a machine which takes input and give you some output. Got it. Now the second thing is neuron. Okay, what is neuron? Interesting. Many of times in machine learning classes, in artificial intelligence classes, we might have heard hundreds of times what is neuron. And sometimes, well, like for me also, it's a sort of confusion. Like I interpret neuron as a physical object, but let me tell you that neuron is not a physical object. It is not a physical entity in itself. For me, or you can say for a general definition of neuron is it's a mini calculator. Mini calculator which takes a set of numbers as input, set of numbers as input, okay, multiply and then multiply these numbers with its importance, then add a additional number, add a additional number, okay, uh, that is it. That is it, right? The definition of neuron is it's a mini calculator, right? It's a mini calculator, and the work of this mini calculator is it takes a stream of inputs. Okay, it takes a stream of inputs, and after taking stream of inputs, it multiply that stream of inputs with its importance. Every number we get in neural network will have its corresponding importance, and we take this importance number with the input number, multiply them, add them together. After adding them together, we add a additional number, and it will give you a output, and a neuron gives you one output. This is important. So if you have to visualize how a neuron looks like, for me a neuron looks like something like this, right? It is a calculator. It takes a stream of input. It takes a stream of input, and I imagine this stream of input as a single dimensional array, right? 1D array. It can be 1, 2, 3, 4, 5, something, something. And for it, we will have a importance array associated with it. For one, we will have some importance number, for two, importance number, and all like X, Y, Z, alpha, beta, whatever. Now, what we will do is that after like a neuron will take input number and the importance of it, and after that it multiplies both of them, like it multiplies my input slash its important, right? Multiply the input value with the important, and then add on top of it an additional number, and that will be the output of the neuron. So remember, the thing is we can take n inputs, but a neuron will, sorry, will always give you one single output. So n inputs, one output, and in between it does some calculations, it do some math. That's it. That is why we call it as a mini calculator. Got it? Now the third definition is weights. Okay, so each input is associated with a importance number, with a importance number, and we call these values, these importance values, as weights of the given input, weights of the given input. So if there are 10 inputs, then there will be 10 weights. If there are 100 inputs, then there will be 100 weights. And uh, weights tell us how important that particular value is, how important that particular input is. That particular input is for our neuron, okay. And initially let me write it. Initially we assign random numbers, we assign random numbers in weights, right? So if your input looks something like this, like 1, 2, 3, 4, and then we'll have weights associated with it, like 0 0.5, 1, 2, and 10. So you can see that for this given input and weights for our neuron, 4 is the most important number because it has the highest weight. And initially this weights, this array, right, this weight array is very random numbers. We like put a random function, which is a Python library. We just put like randomly in this array, random numbers will come up. And as we train, as we change our input, we change our weights, right, we get the most optimum weight. We get most optimum numbers instead of random numbers. We get here correct weights, right? The correct weights. Got it? So this is it. Weight is basically each input will have associated value, and this important values is nothing but weight, and weight tells us how important a value is, right? How important our input value is. Okay, initially we assign everything as random. In the given weight array, everything will be random, but as we move along in our training process, right, we will have perfect weights which aligns with our true output. Okay, so weights are changeable, inputs are not changeable, true answer is not changeable, the working of neuron is not changeable, but what changes is weights. All right, we can change the values in the weight array. Okay, the fourth definition is bias. Okay, so after multiplying, I have said you right, after multiplying weights with its corresponding input, and adding them together, after this, after doing this first step, we add a additional number. We add a additional number, and we call this additional number as bias. And why are we doing it? Why are we adding bias? You will understand it once we go in the midst of the lecture. But for now, understand that it acts as a starting point for our neural network, for our neurons. Okay, and it is also initially random. Initially it is bias is also random, and from random we will try to match or get the perfect value, perfect bias value, as we move along in training. As we move along in training, we will see like what is perfect bias, what is perfect weight. Okay, so this is it. Every time like we have our true answer, right, we have our output, we know that there is a gap. To reduce this gap, we put random values in weight, not just random values. We will get how much we need to change and all from chain rule, but we keep on changing the weights and biases value, and the value which because of which the output is matching with true answer, that value of weights, that value of biases is known as perfect output. Sorry, perfect weight values and bias values. Okay, now another definition, right? These are the terminologies which you have to understand to in order to start with our concept, with our math, right? That is why I'm taking time to explain each and everything in detail. So the next thing is sigmoid function. Okay, what is a sigmoid? Sigmoid is a special type of function, special type of function slash squashing function, which is used to express the value of output, of neuron, output of neuron between 0 comma 0 to 1, and it tells this value, whatever the sigmoid we get, right, this value tells how confident the answer of our neuron is. The answer of our neuron is with respect to our true answer. Okay, so here, if you see here what we are doing, what a neuron is doing, if you see here, it is first of all taking all input. Okay, let's say the input is X, right? It is taking all inputs. It is multiplying that inputs with weight. And after multiplying, I'm adding something additional number called as bias. And this is my output of the given neuron. Right, this is what I'm doing, right? If you see the output of a neuron, this is the output of a neuron. If I represent it mathematically, then first of all, the first step I'm doing is I'm taking all inputs, multiply with its corresponding weights, then add an additional number, and this is my C. This is my output of the given neuron. This is the mathematical representation of working of neuron. Now after getting Z, what I'm doing is that I'm putting my Z in a special squashing function which gives me value between 0 to 1. And what is the representation of my sigmoid? What is the mathematical representation? It represents something like that. Sigmoid of Z is equals to 1 divided by 1 plus E of minus Z. Here E is equals to minus 2.71. So this is the mathematical representation of sigmoid. And why we are using sigmoid? Sigmoid gives me output in between 0 to 1, and also it tells how much confident our answer is, how much it is near to our answer. If it gives you 1, then it tells you exactly that your true answer and your output are same. If it gives you 0, then there is a vast difference. They are in opposite directions. Okay, got it. So here, if Z is equals to positive, if Z is equals to positive, then my sigmoid of Z tends to 1. Right? If Z is negative, then sigmoid of Z tends to 0. And here Z is 0, then sigmoid of Z would be 0.5, exactly 0.5. Okay, got it. Now, here's the thing, that it tells you how much confident the neuron is, the output of neuron is, right? If it exactly 1, then it is perfectly aligned with true answer. If it is 0, then they are in opposite directions. You need to do something to get closer to your uh, true answer. Okay, got it. Now, here's the thing. Now, we call this sigmoid as predicted output. Predicted output. Remember the terminology. Now, I have been talking about loss, right? Loss. What is loss? Loss is the value, or loss tells us, you can say it tells how far the output is with respect to my true answer. And I represent loss as L is equals to my predicted output minus the true value whole square. And remember, true answer will always be 1. Okay, and my sigmoid lies in between 0 to 1. So loss represent, this is the mathematical representation of loss. Here, like we will put the predicted value minus true answer and square it, and whatever the value you get, that is the value of loss. And the more higher value of loss you have, it tells you more how much away you are from true answer. Okay, in one sentence, if I have to summarize it up, a neuron takes a stream of input, it multiplies the stream of input with its corresponding weights, and then after multiplying, it adds them together. Each input with its output, multiply them and add them together. After adding them, add additional value called as bias, right? When you add, you will get the output. You will get the output of the neuron. Now take this input, take this output, put it in a squashing function. It gives you predicted output between 0 to 1. And this squashing function tells you how confident your neural network is about the output. Okay, so after getting squashing function, we calculate loss. Okay, after calculating loss, we will apply something called as chain rule, and chain rule tells exactly how much you have to change your weights and biases. Okay, understood? So these are the definitions. This is our part 0 of our lecture. Now let's move into a bit of math. Okay, so here the math is first concept in math is now we are going into our mathematics. Okay, till now we have talked about what is the working of neuron, and then we have explored definitions like what is a neuron, weight, bias, sigmoid, loss, and how do we mathematically represent them. Okay, and I have talked about like visualization as well. Now let's talk about math. The first concept in math is derivative. What is a derivative? A derivative is nothing but a basic idea of if you nudge your input a little bit, then how much your output is changing. That thing is known as derivative. So if I have to write it here, if I nudge my input a little bit, then how much my output is changing. How much my output is changing and in which direction, whether it is increasing or whether it is decreasing, in which direction it is changing. Okay, here if you see my output is loss, right? My output is loss. At the end, I'm trying to minimize loss, and the inputs are weights and biases. So can I write that a derivative will tell me how much change I have to do in weights and biases in order to minimize loss? I can tell that, but let's not directly go there. Let's go step by step. So if I have to write this definition, which I have written in my whiteboard, I don't know why my screen is keep on hanging and stopping, but if I have to write it, then I'll write it something like this. If there is a function, let's take old function f of x is equals to x square. Okay. And let's assume that at x is equals to 3, my f of x will give me 9. Okay, now what I'll do is that, what is derivative? Derivative is we take input, change it very little, and observe how output is changing. Okay, so if I take my x as 3.001, then what will happen to my f of x? You will see x square, right? It will be 3.001 whole square. So if you write it here, then it will be something like this: 9.00601, something like that. Now how much it has changed? So if you see, my input has changed from 0.001, I have increased my output, and the output we got is 0.006. So how much difference is there? To calculate difference, directly divide output divided by input. So it will give you 0.006 divided by 0.001. It means that exactly 6 times the output has changed if I change my input a bit. Okay, so at x is equals to 3, whatever the change you do, right, it will increase by 6 times as the output on the output end. Okay, and if I have to represent this thing in mathematical terms, then we represent differentiation as like this: d of the given input, which is our function, with respect to my this is f of x is the output with respect to my input. How much the output is changing with a little increase in my input, that is differentiation. And here you can write it: differentiation of x square divided by dx, and we know the formula. It will give 2x as output. And if you write at x is equals to 3, you will get 2 into 3, you will get exactly 6. And from manually, we got the same thing. And from differentiation, you got the same thing. It means that at exactly x is equals to 3, if you change the output, then it will increase by 6 times, right? So if I have to draw the graph, it will represent a parabola, right? If I'm not wrong, yeah, parabola. Something, it will be something like this. It will touch origin. Okay, at exactly 3, my line would be something like this. And this is a very small change, very 0.001 change. And the rate of change happening is 2x. It is increasing by 2 times every time. Okay, so this is the thing. And in simple terms, if I have to tell you derivative is nothing but how, in this case, if I take this case, if f of x is a function, which tells you about output, then differentiation is nothing but differentiation, comma derivative is nothing but it tells you that how much f of x is changing with respect to x. So this is the definition of derivative. It tells you that if you nudge input a bit, then how much your output is going to change. This is the definition of a derivative. Now, if you are clear, then let's move to another topic, another interesting topic in math itself, which is partial derivative. Okay, so what is partial derivative? Suppose in the above example, I have taken one single variable, right? One single variable, I have taken f of x is equals to x square partial derivative. But imagine a case where there are multiple derivatives, right? Like f of x is equals to x square y. Then how I'm going to calculate the derivative, because there are two variables. Then in this case, if this is the case, then what happens, partial derivative tells us, right? It tells that if you are calculating with respect to x, then consider all other variables as constants, right? And similarly, if you are calculating with respect to y, then consider all the variables except y as constants. This is the definition of partial derivative. And how do we calculate it? If we are calculating differentiation with respect to x, then my output would be d of dx. I will give you 2x multiplied by y. So I will give you 2xy. Okay, this is with respect to x. Now, if I take with respect to y, then d of f of x comma y, here f of x comma y, function representation, f of x comma y divided by dy, it will give you differentiation of x square y by dy. It will give you exactly x square. Okay, so if you write it, if you want to calculate like how much x is changing, like if I take at x is equals to 3 and y is equals to 2, then you will get it as 2 into 3 into 2, 4, 12. Okay, this will be 3 square, which is 9. Here you can tell that yes.
You're recording.
What?
Nothing, nothing. I thought you were not recording.
What? I'm recording.
I thought you did not start recording.
No, I have started. Okay, so here you can see that at x is equals to 3 and y is equals to 2, x is changing 12 times with respect to a little change in the function is changing 12 times with respect to a little change in x. Right, at x is equals to 3, y is equals to 2, the given output is changing 9 times with respect to y. Now you might ask, like, Jabir, I have understood that like we are changing weights, right? That is why we have talked about derivative. Now why do we need partial derivative? The reason is that if you take a neural network, right, a neural network, not just one neuron, a network, you might have millions of weights, right? And your work is to calculate the how much weight is how much the loss is there, how much loss you are getting in little change of one particular weight. So in that case, partial derivatives are really important. So what we'll do is that, let's say I have multiple weights, W2, W3, like this, I have 10 different weights. Now, if I want to calculate that, if I change weight one only, then how much loss is getting minimized, right? So if you want to calculate with respect to W1 only, then you keep all other things constant. Here is where partial derivatives is used. So I hope you are clear with derivative and partial derivative. Now the third topic and the main core, or you can say heart of the topic, is chain rule. So chain rule tells us, let me tell you this analogy instead of going into complete math. So in real world, right, we might have different nested functions. For example, let's say, sure, I haven't seen math this much hanging. So let's say I have a function y is equals to x plus 1 whole square. Okay, so I can directly like expand it and get a function in, like easily I can get a function y is equals to, I can expand this. But can I imagine my given expression something like this? Can I imagine this as u is equals to x plus 1? So my y would be u square. Okay, now now uh, like to calculate dy by dx, so I can write that d here, let me write y is equals to u square, right? Y is equals to u square. Now if I'm asking like what is the value of dy by dx, if I gave you this expression, right, just forget, let me I don't want to create any confusion, let me just erase everything. Okay, let's say I have a nested function like this. Okay, so here y is equals to u square, and I'm asking, my question is dy by dx. Tell me dy by dx. So you don't know, you will say like, Jabir, there is no x here, like there is no relation between y and x. So how can I calculate dy by dx? I can calculate dy by du, right? So how can I calculate? That is the main question. So here, let's say I have given you u is equals to x plus 1, right? And my need is to calculate dy by dx. So you can see there is no direct correlation. There are two different functions in itself. So what we will do is that first of all, you calculate du by dx and calculate dy by du, right? Step one is calculate this, and step two is calculate dy by du, because from this expression, I can calculate dy by du. From this expression, I can calculate du by dx. So first of all, let me calculate du by dx. So it will give you d of x plus 1 divided by du. It will give you 1. That's it, right? And the second expression is dy by du. So dy by du will give d of u square by du. It will give you 2u. Okay, now to calculate dy by dx, right? Instead of putting this here, substituting and expanding square, you don't have to do anything. What chain rule tells you is that just take the local derivatives. You have du by dx, you have dy by du. Take dy by du, multiply it with its another local derivative, du by dx, and whatever the answer you get, right, that answer will be your final answer, will be your global derivative, which is dy by dx. Okay, can we verify it? Let's verify it. So here, let's assume that x is equals to 2. So here, first of all, I'll go with my chain rule. So my chain rule says dy by dx is equals to dy by du cross du by dx. Okay, so if I put the value right here, this will give me 1. Okay, this is 1, and this will give me 2u, and u is 2 into x plus 1. Sorry, God, 2x plus 1. Okay, so if I write x is equals to 2, then it will be 2 into 3, it will give me 6. So this thing will give me 6. Okay, so dy by dx, the final answer would be 6 at x is equals to 2. This is from chain rule, right? At x is equals to 2, I got from chain rule as this. Now, if I directly apply, like instead of substituting or following chain rule, if I from direct, let's check the answer. So here y is equals to u square. So it will be x plus 1 whole square. It is x square plus 1 square plus 2ab, 2x into 1. So y would be x square plus 2x plus 1. Now if I have to calculate dy by dx, then I can calculate here. From now I can calculate. So it will give 2x plus 1 and sorry. Yep, 2x plus 2 actually, not 1. Okay. Now if I write x is equals to 2, then it will give 2 into 2 plus 2. It is exactly 6. So from my direct substitution, it's a long method, and from my chain rule, it's a very two-step process, and both give me the right answer. Okay, so this is the thing. This is how we use chain method. This is how the chain methods works. Now the question comes, like, how are we going to check, or how are we going to use chain rule in our neuron, right? So for that, theory is completed. Right now, theory is completed. Like, this is the theory you need to know: derivative, partial derivative, and chain rule. And I have verified chain rule. Chain rule is working, and chain rule is smaller when compared to this direct method. In direct method, you need to expand and all. Just imagine that we have 100. Then it's a big thing in itself, because you cannot expand 100. So direct method is a bit of like computational method. That's why we don't use it. We go with chain rule. Now here's the question. Here is the question. The question is, uh, how are we going to use the chain rule concept in neural network? How are we going to use chain rule concept in neural network to adjust our weights? Okay, so let's talk about it. Let's talk about how are we going to use it and all. But remember that this is chain rule, and there is something called as backpropagation, which I'll talk. Don't worry about it. Definitely in Build Sunday lecture, we will take a layers of neural network. There we will talk about backpropagation. But remember that chain rule is for one neuron, right? If you have layers of neurons, then you will apply the chain rule again and again repeatedly, and that repetition is nothing but backpropagation. Okay, so let's talk about implementation, how it is useful. So the third concept, I think third only, right? Yep. Yeah. So 0 is definition, 1 is this, second is our uh, application. So talking about application, how it is applicable in neural network, how we are going to use, how to use chain rule. To talk about it, I want you know a bit one more terminology. The terminology is computational graph. What is a computational graph? Listen, in a given neuron, right, we are doing different things. Like, we are taking input, then we are calculating our z, which is the output given by neuron, then we are calculating sigmoid, then from sigmoid we are calculating loss. So we have, for one single neuron, we have different operations. Now if you represent this different operations as single stages, then the representation of each computation happening, the representation of each computation, each stage of computation, each stage of computation, okay, uh, happening, if we represent this, if we represent the each stage of computation in terms of boxes, and arrows are used to represent the flow, to represent the direction of the computation of neuron. Okay, we call this diagram, whatever the diagram we get, as computational graph. Okay, how does it look like? Let me show you. So initially we have inputs. So we represent inputs in a box. Then we are giving this inputs to our function, or you can say to a function which calculates the output of neuron. So it is Z is equals to taking all inputs multiplied by weights, then add them together. Okay, let me write it cleanly. So input multiplied by weights, then add them together. Whatever the multiplication you get, add them together. Then after adding, add bias on top of it. We are doing this step 2. So we represent this in a box. Then we are giving this to a sigmoid function. We are calculating sigmoid of C. This is a box in itself. And from that we are calculating loss. Right, and loss is our final output. So this is the flow of neuron, right? This diagram, this whatever the diagram we got, we call it as computational graph. Okay, got it. So one terminology completed, another terminology. Forward pass. Okay, so forward pass is moving from left to right. So if I move in this direction, right, from left to right, taking inputs, calculating output, then sigmoid, then loss, then we call this as forward pass. So in forward pass, we move from left to right, and what we calculate, forward pass is nothing but moving from left to right in the given computation graph. And what we are doing here, we are calculating prediction and loss. So in forward pass, we move, the point you need to understand is we move from left to right. And in this entire journey of forward pass, we try to calculate two main things. One is sigmoid, which is our prediction. From sigmoid, we try to calculate our loss. These two things are calculated in forward pass. Okay, got it. Now another terminology is backward pass. Okay, so here in forward pass, we get loss, right? We get loss value. Okay, now here I'll just write loss value as something, whatever value we get, right? We get loss value here. In this, we are standing here. Like if you apply forward pass, then we will go from one box to another and all like this. Okay, and we will get loss. Okay, now we got this loss. We got to know that my answer is here and output is here. This gap. Now I want to reduce that gap. How can I reduce? How can I reduce? So I need to go back, right? I need to go back. And how can I go back? That is the main question, right? How can I go back and change the weights? Because this loss, this whatever the loss which is getting generated is because of this and this. I need to change the weights and biases. That is my task. So I need to go back. So backward pass is basically moving from right to left, right to left. And at each stage while you are going back, right, let me draw it with a different ink pen. So backward pass is this is backward pass. And how I move, I'll take this, I'll go back, right? So how I can move, that is the question. So tell to tell how you can move and all, what we do is that we calculate the local derivatives. So let me tell you this. So here the output is loss. And what I'm trying to tell, I'm trying to tell this output is coming from sigmoid, right? And sigmoid is coming from this equation. So if you see, imagine this is y, this is u, this is x. I want to know how much y, how much change in y is impacting x. I can't directly tell because there is something in between, right? There is like in intermediary function. Okay, so I can tell. Can I I know that I can't directly tell a relation between y and x because there is something in between. So can I tell the output, which is here x, right? In this diagram, which is here x, is getting affected by u and u is getting affected by y. But I can't directly tell how y is impacting x. And I need to know how exactly y is impacting x. Okay, that is my task. But I can't directly tell. What I can tell right now, what I can tell, if you see, I can tell how u, which is our input, is directly impacting our output. And what is this? This is our derivative. If you see like this, so backward pass is nothing but a derivative. So we calculate local derivatives. Local derivatives means we calculate how, okay, we calculate, let's say box 1, box 2, box 3, right? So we calculate how box 3 is being affected by box 2. We can tell that, right? We calculate that, we put it aside, right? Calculate it and put it aside. Then again calculate how box 2 is being affected by box 1. Calculate it, put it aside. Now our goal, what is our goal? What is our goal? Our goal is to tell how box 1 is impacting box 3. How we can tell? So if I have to like represent and go back to our old concept, what is this? Here we need to calculate, we want to calculate the impact. We have y is connected with u is connected with x, and we want to tell how y is impacting x. That is our goal. But we know we can't directly tell. That's why what we did, we calculate this, and whatever we calculate, the differentiation, take this and this, multiply. So whatever the, so to tell how one is impacting box 3, what we do is that to calculate the derivative of box 1 with respect to the derivative of box 3, what we do is that we calculate box 2 derivative with respect to box 3, multiply by box 3 box wait. So we can tell box 3 derivative output with respect to box 2. Okay, box 3 with respect to box 2. Let me write it correctly. So box 3 we can tell with respect to box 2. Okay, I know I'm telling boxes again and again confusing, but don't worry, it's a very basic thing if you see. And we know how box 2 is getting impacted by box 1. So if you put it here from this chain rule, you can exactly tell how much weight you need to change to get proper loss, to get your true answer. Okay, got it. Now let's do a numerical, right? Numerical is very much needed. Okay, so what I'll do is that I'll take an example. I'll take example of input as 4, weight as, wait a second, like I think I do have a numerical in hand, which I did before coming to lecture, and let's use that numerical. So what is our loss? Like first of all, let's assume that x is equals to, you can take anything, weight is equals to 0.5. I'm not using my own numerical. B is equals to 0.1. I have taken random numbers. Then let's calculate z. I'm moving in forward pass. First step is forward pass, right? So in forward pass, what we do, we calculate z. Z is equals to 4 multiplied by weight. Let's take our numerical because we need to calculate e to the power of minus z as well. So I have taken x is equals to 2, weight as 0.1 and 0.2. So multiplied plus 0.1. So it will give you 0.5 multiplied by 2. So 1 plus 0.1, if I'm not wrong. Okay, so it will give you 1.1. So my z would be 1.1. Now the next step in forward pass is to calculate my sigmoid. So I'll calculate sigmoid of z. Sigmoid of z is equals to 1 divided by 1 plus e of minus z. So it will give you 1 divided by 1 plus e of minus 1.1. it will be around, what is the value I got? Sigmoid as 0.75. So it will give me 0.75 as output. Now, this is the final step in my forward pass. So the value is A, which is my Z, right? Sigmoid of Z. So let me control, okay. Sigmoid of Z minus my true answer, which is Y whole square. Okay. And I know, like here, my true answer will be always 1. So if I put it here, then it will give 0.75 minus 1 whole square. So it will give, like, how much it will give? It will give you 0.06, right? 0.06. So this is my complete forward pass. Forward pass is completed. Let me, yep, okay, this is my forward pass. Now after the next step is to do backward pass. We need to calculate local derivatives. So if you draw the formulas, the second thing is backward pass. So I am standing at the last box, which is my last box. So what is the formula of loss? A minus y whole square. And here what is changing? Y is constant. And I need to know, I'm representing A as sigmoid. Instead of writing sigmoid of C minus Z, instead of confusing, I'm just representing it with a letter. Okay, so if you see here, right, our thing is let's expand it. So A square plus Y square minus 2AB, right? 2AY. So our L will be looking like this, 2AY plus Y square. Okay, now if you apply, our thing is, the thing which is changing is A. So we will find the loss with respect to sigmoid. So the first derivative is dl by dA. I will give you 2A minus 2. Right? Yeah, and this will be 0 because this is a constant with respect to A. So this is our output. And what is our sigmoid? 0.75. Apply it. So you will get at A is equals to 0.75. We know A is equals to 0.75, then you will get 2 into 0.75 minus 2. It will give you like what? Uh, minus 2, yeah, minus 1. Yep, correct. I'm doing correct. Okay, so it will give me minus 0.49. Okay, so what we will do is that this is the formula dA by dL is equals to 2 into A minus 1. Okay, and at A is equals to 0.75, I get my output as 0.49. Put it in a box. Okay, I have put it in a box. One derivative is completed. Second derivative, how my sigmoid is changing with respect to my output, which is Z. So what is the relation? The relation is that sigmoid of Z, which is A, is equals to 1 divided by 1 plus E of minus Z. So it will be D of 1 by 1 plus E of minus Z divided by DZ. So you don't need to worry of how we are getting formula, but the formula is for this derivative is that if you are doing dA by dZ, then it will be A into 1 minus A. This is the standard formula. If you open Google and see, this will be the one of the formulas which we studied in differentiation, right? So apply standard formula. You don't need to worry where it came from and all. Just apply that. So our output would be dA by dZ is equals to A into 1 minus A. Okay, and at wait one second. Yeah, it is correct. It is correct. At A is equals to 0.75, our answer would be 0.75 into 1 minus 0.75. So it will give you 0.18 as answer. So this is the formula. This is the second derivative, not formula. This is the second derivative we got. So the derivative of dA by dz is this. And at A is equals to 0.75, this is the value we get. Now, our goal is to calculate how. Before going to that, we need to calculate Z as well, right? So here the third derivative, Z is equals to input multiplied by output plus B. So what is changing here? There are two things changing, weight and bias. If you remember partial derivative tells if you want to know weight change with respect to weight, then make everything constant. If you want to know change with respect to bias, then make everything constant, other things constant. So here the third derivative is dz by dw will be input multiplied by 1 plus 0. So dz by dw would be input. And what is our input value? The input value is 2. So it will give me 2. This is our third derivative. This is our 3.1. Right? Okay, let me write it. First derivative, second derivative, and third derivative. Now another derivative is how z is changing with respect to b. Okay, so d of iw plus b divided by d of b. It will give you 1 because this thing is constant. Constants are 0. So it will be 1. So here dz by db is equals to 1. That's it. This is our derivative 3.2. Now what is our goal? Our goal is to calculate this dl by dw and dl by db. How loss is changing with respect to weight, how loss is changing with respect to bias. So can I write this equations, see these equations properly, that dl by dw is equals to, first write the at lastmost derivative, this thing. So dl by dA multiplied by second derivative. So dA by dz multiplied by dz by dw. dz by dw. Can I write it like it? Like that. So this is the derivative. This is the equation for our neural network. This is the chain rule. And it tells you exactly how loss will be with a little change in W. Okay. And let me write it here. L by dB would be, write the outermost derivative dl by dA cross dA by dz cross, instead of, now you're checking with respect to B. So here that is why dz by dB will come. Okay, and it tells you exactly how loss is changing with respect to change in B. Got it? Now let's calculate as well. What value we got here? It gave us equation 1 0.49. So 0.49 multiplied by 0.18 multiplied by 2. So it will give us 0. Wait a second, this is minus, right? Actually, I think this is minus, I think. Yep, minus 0.9. Okay, so this will give us minus 0.187. It means that the value of this derivative is this thing for the given inputs. Now what this value tells us? It tells us that to minimize loss, I need to change my weights. I need to reduce my weights. Okay, and by how much I'll tell you, but it understood that negative means reducing weights is preferable in order to minimize loss. Now if I have to calculate dl by db, it is like minus 0.49 multiplied by 0.18 multiplied by 1. It will be 0.09 minus 0.09. It means I need to change weights. I need to decrease bias as well, right? I need to decrease weights. I need to decrease bias. But I need to, like, from the values, you can exactly tell that the change, the decrease in weight should be more than biases. Okay, so this is known as chain rule. Now, what is backpropagation? Backpropagation is a term which most of computer AI/ML scientists use, and backpropagation is nothing but applying chain rule for like layers of neural network. If you take neural network, you will not have only this like one layer, two layers, something like that. You will have input, okay, and layer one, and again in that you will have layer two, again in that layer three, and like this you have millions of layers of weights, layers of biases, layers of neural networks. So it's a big thing in itself. And finally, you will get loss, predicted value, and then loss. Now, what they'll do, backpropagation is nothing but for this entire network, for this entire system, calculating chain rule, putting chain rule on this network. This is known as backpropagation. Backpropagation is nothing but on scale. Got it? Now, I think that's pretty much it. And there is also one more thing which I want to talk about, that sanity rule, sanity check. Sanity check is a verification method which tells that this derivatives you got is correct or wrong. So what we will do is that we take a small change in weight. Let's say I'm taking change in weight as 0.01. So we will reduce weights like existing weight, we will reduce it by 0.01. We will increase it by 0.01 and we check whether we are getting this output or not. If we are getting this output, then our differentiation equation we got right, this combined like set of derivatives, there are multiple derivatives here, so this set of derivatives are working. And I want to give you one more terminology, last terminology of the session, gradient. Gradient is nothing but if you have least of derivatives doing some operations with one another, then you combine them, you combine this list of derivatives, and instead of calling like multiplication of derivatives or operation of derivatives, you call this list of derivatives as gradient. Okay, and you have understood, right? Like this is telling us that I need to reduce it, but the question comes, how much I need to reduce, how much? So for that we will see in next lecture, but I hope you have understood that how chain rule is applicable in neural networks and how we use them. Now let's talk about the algorithm of the next lecture. So the algorithm is, I think this is 4. Yep, algorithm is first put forward pass. You have neural network. From forward pass, you will get prediction and loss. Right. Second, apply backward pass. And from backward pass, you will get your local derivatives. Okay. After getting local derivatives, wait 1 second. Okay. So forward pass move from left to right. And in forward pass, what we do? We calculate our sigmoid, comma loss, comma output as well. We do these things. We calculate simple uh, like equations. Now, after that, we apply backward pass. In backward pass, we move from at most like last block right to left. And what we do here? We calculate local gradients, local derivatives. After calculating local derivatives, step 5 is calculate gradient. Gradient. And gradient is nothing but least of derivatives combined together. Here we are combining derivatives, right? 3, 4 derivatives. We call this combination as a gradient. So least of derivatives is nothing but gradient. Calculate gradient and using gradient descent, change the value of weights and biases. And when you do that, right, loss will be minimum. It means error would be minimum and you are near to your true answer. This is what we do. Okay, I hope you got the point. And I have underlined one thing: gradient descent, very important. And we will talk about it, not now, not in the next class as well, but sure in the next upcoming classes. But I'll give you a basic example. Gradient descent is nothing but multiply the value of gradient. Gradient is nothing but dl by dw. That is our gradient, right? So multiply the gradient, okay, with a number. It can be 1, it can be 2, it can be 3. It multiply it with a scalar and then subtract it from weights. Subtract it with weights and biases. This is nothing but gradient descent in very simple language. In 130 seconds, I have explained you what is gradient descent, but we will see what is it. But for now, this is the algorithm. The algorithm which is used to train neural network, and we keep on repeating, like we repeat this entire thing in a loop until unless we reduce like loss and go to our true answer. So first thing is apply forward pass, calculate EAL and Z, then calculate like do backward pass, calculate local derivatives, and from chain rule you will get your gradient, and using gradient you will know in which direction and how much. Okay, this is it. This is the algorithm. And we will apply this algorithm in our next class. So yeah, and also in next class, we will not take one neuron. So we will see there what is backpropagation and all. We'll take 3, 4 neurons, and then we'll see how a combination of network of neurons will work. And we'll try to solve a game. It's I'll talk about it in next lecture. Let's not extend this lecture. It's already 1 hour 30 minutes lecture. So I hope you got. If you have any doubts, you can ask me right away now.